Hello. So this is the last class of the semester, and what we have to do today, my goal is to speak about stationary Fourier integrals and stationary phase approximation, and to provide for you more examples of the two-time perturbative analysis. What I really don't know is what to begin with. So, okay, let's begin with the Fourier, with the stationary phase approximation in the Fourier integrals. So, in general, what we would like to analyze again is our integrals that are now of the form integral from a to b of f of t e to the I x psi of t dt. So the difference between this and Laplace integral is this I, right? And as I told you, this implies that when we have Laplace integrals, when we have no I, it means that when psi has a maximum, you have something which is exponentially large, and the main contribution to the integral will come from the vicinity of the place where psi has a maximum. Here it's a different story, although it seems because of the I, right? So what we have here is something that oscillates. We will see that the result, the end result is quite similar to the result in Laplace integrals, but in order to do that, we have to go through a few steps, right? So to begin with, let's consider the integral from 0 to 1 of e to the I xt divided by 1 plus t dt. Right? You see? That's an integral. And we want to approximate this integral when x goes to infinity, when x is large. Okay? We want the asymptotic behavior of this integral when x is large. So one technique that we are already familiar with, and maybe it will be a nice example of using this technique, is to implement the integration by parts. So this integral is equal to the integral from 0 to 1, of 1 over 1 plus t ddt of e to the I x t dt, but I have to divide by ix, right? Okay, well, I can write this as minus I over x. Doesn't matter. Okay? Do you agree? And okay, so the first contribution, I have minus I over x here, and I have a 0 to 1 of e to the I xt, minus or plus, so it will be plus I over x, integral from 0 to 1 of e to the I xt over the derivative of z, right? Which is 1 plus t squared, and I guess that I have an extra minus here because I took the derivative of z. Okay, if I'm doing mistakes, please.
Wait, the first term should also be divided by 1.
What?
The first term should also be divided by
Sure. 1 plus 2. Yes. I just forgot. Okay? So, what we have obtained is, okay, now note that the lower bound also give us a contribution. So what we are going to get? We have minus I over x times the upper but the upper limit is e to the ix over 2 minus the lower limit is simply 1. Right? So this is our first approximation, and now we have minus I over x integral from 0 to 1 of e to the xt divided by 1 plus t squared, which I can write as 1 dt of e to the ixt dt divided by ix. So the I goes away and I have an x squared. Okay? Now,
Should be plus?
should be plus
No.
y plus.
No, it's okay.
No,
It's okay.
it's I over I.
Okay? Again, it's your responsibility to cut my mistakes. So, what we have until now, we have I over x minus e to the ix over 2x. That's first two terms.
I. You should be both
I. And now we have minus 1 over x squared times, and okay, so this will give us the first approximation. It will be from 0 to 1 of e to the ixt now divided by 1 plus t squared. Okay? So I have 1 over x squared times what? Times
E to the I.
e to the ix
Over 4
divided by 4 minus 1. Right? And then we have the next term, of course, will be plus 1 over x squared integral from 0 to 1 of e to the I xt divided, now I have 1 plus t cubed, and I have a minus here, and I have an extra 2 here, I think. Something like that.
dt.
What?
dt.
dt. Okay, so you see that okay, let's just check ourselves now. I have I over what's going on here? Yeah, I have I over x minus I over x times e to the ix. This is that one, and then we have minus e to the ix over 4x squared plus 1 over x squared minus 2 over x squared. Blah, blah, blah. Okay, that's fine. That's fine. And, okay, so you see that these two terms are going like 1 over x. And then we have another term that is going like 1 over x squared. So it's subdominant in the limit when x is very large. Okay?
So it's because the ix is.
E to the ix is plus minus 1.
Yeah,
Right?
It's
It's what?
it's bounded, so you can just.
It's bounded, yeah. And then we have something like that, that is, again, this cannot be, in any case, this term cannot be larger than 1 over x, right? Because of what? Because I can write it as 2 over x squared. Let's define xt to be q. Okay? So I have 2 over x squared, the integral from 0 to x of e to the iq divided by 1 plus q over x squared cubed q over x cubed divided dq over x. Okay, so we have here x cubed, and this, if x goes to infinity, this will provide me a constant, because I have an integral from 0 to infinity of e to the iq divided by nothing, by 1, right? So this will give me something which is x independent, I guess. So I will get e to the I 2 over x cubed. So this will be smaller than this and smaller than that. Okay? And therefore, it's a fair expansion, and we can continue with that to infinity if you like. Okay? This is just integration by parts. Are you okay with that? Okay. So let's try another example. Now we want the integral from 0 to 1 of e to the ix t times the square root of t dt. Let's make sure that this is indeed the case. Yeah. Okay. So we want to use integration by parts again. So we write it as the integral from 0 to 1 of square root of t d dt of e to the xt divided by 1 over ix. Again, minus I over x. Very good. And this will give us minus I over x, 0, 1 of square root of t e to the ix t minus plus the integral from I over x, the integral from 0 to 1 of e to the ixt, but now I have to take the derivative of square root of t, which is 1 over square root of t, and I have 1/2. Something like that. Okay? Now, this is a legitimate thing, because here I have minus 1 over x times e to the ix. That's and I have no contribution from the lower limit, because
Minus I.
minus I. Yeah. This is the contribution from here. Now, what about the contribution from here? Can I continue with the integration by parts?
No.
No. Why? Because if I will try to use integration by parts, then I will say this term
Yeah, we'll get
is I over 2x, the integral from 0 to 1 of 1 over square root of t d dt of e to the ixt dt, right? And I have to divide here by another ix, so I will have 1 over x squared, right? But now I have a problem, because if I'm taking just the first term, it will be 0, 1, plugging the limits in e to the ixt over square root of t, and the lower bound will give me something that diverges. Okay? So I was able to use one step in the, but clearly this integral do not diverge. There is no reason for that to diverge. It's just a problem of the integration by parts technique. But I have now a bankruptcy of the integration by parts. I can't continue with the integration by parts. But I can still say that this integral, right? So I want to estimate this integral. Okay? I can write it as I over 2x, and again I will define q as x times t. You see? And what I will have here is an integral from 0 to x as x. You see? from 0 to x over e to the iq divided by square root of q, but t is q over x. So this is square root of q over x, so I have square root of x here, I think.
And when you take x to infinity,
Wait. No, because I have, okay.
3 halves.
This is q over x, square root of q over x, but now I have dq divided by x. Okay? So all in all, I have I over 2 x to the 3 halves. You see? X to the 3 halves times the integral from 0 to x of e to the iq divided by square root of q dq. Okay, now, so first of all, most importantly, you see that I will get a contribution, no matter what this integral is, I will get contributions that is going like 1 over x to the 3 halves. This is an indication to the bankruptcy, to the failure of the integration by parts scheme, because the integration by parts provides me integer powers of x. Okay? Instead, what I can do with that,
take x to infinity.
right? What?
Is to take x to infinity.
Exactly. So now when x goes to infinity, I can approximate it by the contribution from x goes to infinity. And when x goes to infinity, this is the integral from 0 to infinity of e to the iq over square root of q dq. Now, what I'm doing with such an integral,
Use complex.
I am using exactly.
What we
I am shifting the. I will shift, right. If this is real q, and this is image q, right. I want to shift the integration from this path to infinity to that. So I would like to integrate not over q, but over I times q. Right? And if I'm integrating over I times q, then I will get the integral from 0 to infinity of e to the minus q divided by the square root of I times q di times q. Okay? Now, so first of all, what about the i's? I have an I here divided by square root of I. So I should take one square root of I outside. I have here square root of I. Right? Square root of I, by the way, is e to the I pi over 4. Okay? And now, what is this integral? What remains is a gamma function. Is a gamma of 1/2. Right? So what I obtained is I have here I over 2x to the 3 halves times e to the I pi over 4 times gamma of 1/2. That's the rest of the... No, okay. This is not the rest of the integral. This is asymptotic, the asymptotic behavior as x goes to infinity. You see? If I was doing it for finite x, then it was a complete solution. But now all we can say is that the integral we are trying to estimate is asymptotic to what? To minus I over x times e to the I x plus or minus, maybe I have lost something.
But the square root of I has 2 branches. How do you know which branch to take? The square root of I has 2 branches.
Of course.
How do you know which one to take?
The one that converges. I mean, the other branch will diverge. It will be e to the q times.
No, I mean, you have e to the I pi over 4. You can also have e to the I 5 pi over 4 to the other side.
No,
Because I is e to the...
no. I replace q by iq.
You integrate
No.
from 0
Not
to
by
infinity.
minus iq.
No, I meant the square root
And I
of I
replace-
itself. You have the square root of I.
No.
It doesn't necessarily equal to e to the I pi over 4. It has another branch of e to the I 5 pi over 4. How do you know which one to take?
It's always
That's
true.
who
If you have
cares?
the square root
כן,
of
אבל-
25, it's plus minus
Who
5, you
cares?
will take plus 5.
You can.
כן, אבל פה זה מוגדר בממשיים, זה מוגדר ככה חיובי, פה זה לא בהכרח מוגדר במורכבים.
Okay,
מתמטיקאים מתייחסים לזה.
fine.
לא יודע.
So this was an introduction to the topic of Laplace of Fourier integrals. Okay. Now to the real issue. I mean, to okay. So now let's consider a generic integral of that form. Okay? A. There is a theorem by Riemann and Lebesgue. How to spell Riemann-Lebesgue? I have no chance. Okay. So Riemann with double N
Yes.
Yes. and
אם יהיו
letter by letter
S קטן.
Lebesgue. Okay? And what Riemann and Lebesgue gave us guarantee for is that this I of x, is going to 0 as x goes to infinity. Why? Because, as I told you last week, because the oscillations will kill the integral. Okay? You see the point. What are the conditions for Riemann-Lebesgue theorem to hold? First of all, they want psi. Psi is not a constant. In any finite interval between A and B. Because you see, if psi is a constant, then it's just something that I can take out, and I end up with an integral. I mean, at least in some region. And the fact that x goes to infinity makes no difference. You see? So phi is not a constant. We need f to be something. We need the integral from a to b of f absolute value squared dx dt, so to be finite, and we
Without the equal.
what?
If you want to say that it's finite, it's without the equal.
What?
You wrote less or equal than
Less
it's
than.
much less.
Whatever. And we want the other condition is that psi is continuously differentiable between A and B. Okay, that's a condition. So psi is normal function, but not constant in any finite interval between A and B. And it's it's continuously differentiable, and then everything. Okay, so let's assume that conditions by Riemann and Lebesgue hold, right? The first thing we can do, actually, this has nothing to do with Riemann and Lebesgue, but okay, the simplest way is to use integration by parts. So we can try integration by parts in this case. With respect to this integral, what we are going to get? We are going to get integral from A to B on f of t d dt of e to the I x psi of t dt.
You should divide.
Divided by minus I over x.
No, you should also divide by.
Sorry. Minus I over x times psi prime.
It should also.
No, the psi prime should be here.
Yes.
Sure. Okay? Good. And this will give us, so as a first approximation, we are going to get minus I over x. Here I have a and b. F of t divided by psi prime of t e to the I x psi of t. So the first order approximation is minus I over x. And now we have f of b over psi prime of b e to the I x psi of b minus the same thing with a. Good. Fine. So this apparent, and you can continue and convince yourself that the next time will go like 1 over x squared and so on and so forth. When we expect this procedure to break down?
Then psi has a maximum or minimum in upper lower.
Exactly. When psi prime is 0 somewhere between a and b, not necessarily at the endpoints. When it is 0 somewhere between a and b, this thing diverges. You see?
Meaning you want to find maxima of a minimum.
Now you see that's the difference between. First of all, what is the logic here? The logic here is that when psi prime is 0, what does it mean that psi prime of some point C, say, is 0? It implies that psi changes slowly at the vicinity of C. Okay? Now, you know that why the Riemann-Lebesgue theorem works. The Riemann-Lebesgue theorem works because the oscillations, as x goes to infinity, the oscillations kill the integral. Right? So when psi prime is 0, the oscillations are less pronounced. For any finite x, right? When psi prime is 0, no matter if it's a maximum or a minimum, unlike the Laplace integrals, we don't care about maximum or minimum. Because the point is not that you have a huge peak that gives you the only contribution to the integral. The point here is that you have a location along the interval between A and B where the oscillations are slower. Are you with me? Okay? So this is the case where the integration by parts fails. Okay, and the reason will be, and not the reason, the outcome, as you see, the integration by parts gave us expansion in inverse powers of x. So we have first contribution will go like 1 over x, second contribution will go like 1 over x squared, and so on and so forth. However, because if we have a point in which the function psi is moving slowly, then we are going to get some power of x that will be smaller than 1 over x. Like we will get 1 over square root of x, or 1 over x to the 1/3, or everything like that. Okay? Any questions? No questions. Okay. So the only point here is to understand what will be how to analyze the Fourier integral when we have stationary phase. Stationary phase means that psi prime is 0. So the phase of this garbage is as okay. So let's assume that, okay, so suppose we are here between A and B, or between C and B, and the point of stationary phase is here. Let's assume there is one point of stationary phase of where psi prime is 0. This is A. Psi prime of A is 0. Okay? Clearly, I can divide the integral into an integral from C to A and from A to B. Okay? And so let's take into account only the integral from A to B. So we want the integral from A to B of f of t e to the I x psi of t dt. First of all, and now I'm using the same argumentation that I used before, i.e., I assume that the only contribution will come from the vicinity of A. So instead of taking it from A to B, I'm taking it from A to epsilon.
What is epsilon?
What?
What is
A plus epsilon. Sorry. A plus epsilon, which allows me to write it as a. So first of all, for f, I'm taking the value at A. Or let me, I will do an extra step. So A plus epsilon of f of t e to the I x times psi of A. Now, psi prime of A by definition is 0. So I can write it minus psi double prime of A times 1/2 times t minus A.
Why minus? You said it's
Square.
not necessarily
Ah,
minus or
yes.
maximum.
Whatever. Plus psi double prime, whatever it is. And by the way, when it may happen that psi double prime also vanishes. In which case, you remember in Laplace integrals, we have only even powers. Because we can't have psi triple prime because this implies that this is not a maximum or minimum. Here we don't care.
Yes.
Here we don't care. So in principle, instead of writing in psi double prime, I can write psi, the p's derivative at A times p factorial times t minus A to the power of p, where p is the first non-vanishing power in the expansion of psi around A. I don't care, it may be even or odd numbers. I don't care. Okay. So I'm doing that in second power if you want. I mean, in the book, they are doing it generically with that, right? So we just plug p equals 2 into the problem. Okay. So, and again, what we are doing, so now we will assume that, first of all, we will define, say, S as a distance from A. We plug A here and expand the integration, the regime of integration to infinity. So what we are going to get is f of A e to the ix psi of A. That's just okay. And now we have an integral from 0 to infinity
Why is it?
of.
Yes, why not minus infinity?
No, what's the problem?
No, it's A.
Of e to the I psi double prime of A divided by 2 times S squared, say, ds. I missed something. I have an X here. Anything else? Good. Okay? Fine. So now we have to perform this integration, and again I would like to define S as square root of I times, this s is just t minus a, right? But now I would like to define s as square root of I divided by x psi double prime at a times 2 times, okay, do we have another times u? A variable.
Whatever you want.
Q. Did I use Q?
No.
No, Q. Q.
Wait, you assume that A is
Yes. Okay, let's hope. So what we have obtained is f of a
why did you
e to the ix psi of a.
why did you get a f out of the integral?
Hmm?
F of a, why did you get it out of the integral?
Because I assume that the main contribution is between a and a plus epsilon, so f is not, so I can take f. This is the same trick I did in Laplace integrals. So now I have an integral from 0 to infinity of e to the minus q squared times dq. But wait, so we have other factors here. Times dq.
No, wait, why it's minus?
What?
Why minus?
Because I squared is a minus 1.
No, but the I squared is cancelled with the I inside the exponent.
S squared is I times a. Okay.
So that's
So
another
S is
No, it's what you used before, just you need to add another I.
So we I squared.
is
No,
I
inside the exponent. So
times
I.
psi double prime
Yes, it's minus.
divided by of a. No. I divided by psi double prime of a times x. Times x times q, what else, to the power of 1/2. Right, so s squared will kill everything except that I have e to the minus q.
No, why? Why minus? Why minus? You have I inside the exponent. So this term doesn't cancel that. Doesn't you have I?
E to the I, this times s squared. S squared have another I.
Squared.
Okay.
What's the
Okay.
problem? Okay? Now, ds,
So if you need another
לעשות שתיים.
two,
what? 2. Where is the 2? Here.
Yes.
Okay? So, ds is 2i over psi double prime of ax to the 1/2, right?
Q squared.
And now I have
The Q is
q
no, it's
to the 1/2 minus 1 dq, and we have to divide by 2, so we have the 2 here.
Now, how can you enter the 2? Okay, no.
okay.
You had 2 on the numerator.
So you get a gamma function.
So I will get what I have here is f of a to the I psi of a from the outside. Now I have e to the minus q,
Q.
q to the 1/2 minus 1 dq. That's a gamma function of 1/2, and I have to multiply all that, but by e to the I pi over 4 divided by square root of 2x psi double prime of A. And this is gamma of 1/2. So all in all, I have e to the I pi over 4 f of A e to the I x psi of A over square root of 2x psi double prime of A times gamma of 1/2, which is square root of pi. Yes. Now, so now, okay, now I have to check myself, because in the book, as I told you, they gave the general formula. Okay, so let me just copy the general formula from the book.
Instead of 2 it will be.
So f of A e to the I x psi of A is of course independent of these considerations. And now they are writing e to the I pi over 2p, which is fine because we have 4 here, which is 2p. We did it for p equals 2. Right? If you look here, we did it for p equals 2. So this is that, and then we have gamma of 1 over p over p, and now we have p factorial divided by x times psi p of A, the first term that do not vanish, to the power of 1 over p. Is that formula for p equals 2 equals to z?
Yes. It is.
Yes. Yes. Okay. So fine. So at least we got the correct formula in the p equals 2, and this is a generic formula at general p. Okay. And again, I'm stressing again that I would like to stress that this is here p may be 3 or whatever you like. Good. So so let's try to implement this for a few examples.
So in conclusion, we can say that we don't care about.
And
this
maybe sorry. In a moment I will return to your question, but note that the larger p is. What does it mean physically? The larger p is, the more stationary is the phase at A. You understand that? Right? If the first derivative, at A, the first derivative should vanish. Now, if the second derivative also vanishes, then the phase is even more stationary. And if the third derivative vanishes, it's even more stationary, and so on and so forth. And you see that the larger p is, the smaller is the decay of the integral with x, because without, if we have no point of stationary phase, it will go like 1 over x. This is what we got from the integration by parts. If p is 2, it goes like 1 over square root of x. If p is 3, it will decay like 1 over x to the 1/3, and so on and so forth. So the most stationary is the phase, the slowest is the decay of the integral, and this is because, as we explained, the decay is coming from the oscillations, and the larger p is, the more stationary is the phase, and the oscillations are weaker and weaker. That's and they affect the behavior of the integral at the larger extreme. Okay, so let's start with estimating the integral from 0 to pi over 2 of e to the ix cosine t dt. Yeah. This is the integral, and I want the asymptotics of this integral as x goes to infinity. What can I say?
F is 1.
Okay, so f is 1. What is psi?
Cosine.
Psi is cosine t. And where psi prime is sine t, and where sine t is 0 in the interval between a and b? At 0. Right? So a is 0. And psi double prime is, sorry, this is minus sine t. And psi double prime is what? Is minus cosine t. So psi double prime at a is minus 1. But as you remember, we okay, this is something that I have missed. If psi double prime is positive or negative, this gives me another factor of minus what should I say? What should I say? It's a dependency between I pi over 4 and, I mean, I have a plus minus here depending on the sign of psi prime. Okay. So what I have here is, okay, I can plug it everything here.
You should have plus minus. If you mean that you take, you should also put absolute value of the
Okay, yes. And then I should put absolute value.
because if you don't put it, it's
Yeah.
just plus.
Yes. Okay, so what I will get is just plugging in this formula. So we are going to have f of a, which is 1,
And you should have
e to the ix psi of a, but psi of a is 1, right? Psi of a is 1. So it's e to the ix. And we have gamma of 1/2, which is square root of pi. And we have down here, we have square root of 2, and we have square root of x. And we have this, and maybe because, and we should add the e to the I pi over 4, that is now, I guess, e to the minus I pi over 4.
Don't you need to put f because
Half. Why half?
because it's on the lower bound, on the lower limit, and it's not inside.
No,
It's
but
not
we
between-
did all that for the case where it's in the lower limit. All that
No,
was
we
done.
did it for the general.
Yeah, but I just divided it into 2, and I calculated only the what above the lower limit.
Oh, so okay.
Okay, so
So in general, when you have
yes,
the point inside, the
you have to have
multiply by
2 contributions.
You have to multiply by 2.
Yeah.
It will
If the
be
contributions are identical, yes.
So there can
So
be
it will be square root pi over 2x times e to the ix minus pi over 4.
הם יכולים להיות שונים?
Oh, yeah. Because it can be
Mhm.
odd.
Okay.
What's up to minus?
Fine. Okay, another example. Now I want the integral from 0 to infinity
לא, כי זה הפרידה של I.
of cosine of xt squared minus t dt. Sounds bad, right? Yes. Okay, what should I do?
First time is the next one.
First of all, I want it to be an exponent. How do I do that?
Just Euler.
What?
Euler.
Yes, I am defining this integral as the real part of the integral from 0 to infinity of e to the x t squared minus t dt. That's for free, right? And now I see that what is f? F is e to the minus t. What is psi? Psi is t squared. What?
It shouldn't be e to the I x.
Ah, of course. Sorry. Sure. F is e to the minus I t, psi is t squared. So psi prime is 2t, and psi double prime is 2. Okay? Now, where psi prime is 0,
T equals 0.
t equals 0, so a is 0, and psi double prime at 0 is 2. Okay? And psi at 0 is 0.
Does it matter?
What?
Ah, yes.
So again, we plug in this formula. We have e to the I pi over 4, so I have to take the plus minus, but now it's a plus. We have f of 0, which is 1. We have e to the I x divided by square root of 2 times x times psi double prime, which is 2, so overall we have here 4.
Why e to the ix?
Psi of a is 0.
Okay.
Ah, sorry,
so
it's,
it's just one.
I have nothing like that, sorry. So you're right. Okay? And gamma of 1/2, which is square root of pi. Okay? What?
And you should take the
And I should take the real part of that. So, all in all, what I have is square root of pi over 4x times cosine of pi over 4. Cosine of pi over 4 is square root of 2 over 2. So, square root of 2 over 2. So, it will be square root of pi divided by 8x. I think. Let's check. Yes. Although they wrote it as 1/2 of square root of pi divided by 2x. But it's the same thing. Okay? Now, good. Next example. Next example will be I want to have the integral, which is the integral from 0 to pi of 1 over pi times cosine of x sine t minus nt dt. Okay. Now, first of all, what is that?
Yes, sir. Similar to the second one.
That's a method. Exactly. This is actually Jn of x. Now, note that I want now to estimate it not when x goes to infinity, but when n goes to infinity. Right? I want to calculate the expansion of Jn of x as n goes to infinity.
You can do that by converting cosine to the real part of ei over x.
Okay, of course. This will be my first step. 1 over pi integral from 0 to pi of e to the ix sine t minus I n t. And we want the real part of this animal. Now, what is f?
E to the ix sinus t.
F is e to the ix sine t. Why? Because
n goes
to infinity. And what is psi?
Minus t.
Minus t. Okay? So psi prime is what's going on here? Psi prime is
This breaks in this case, we just don't need this approach at all.
wait.
Because the integration by parts is really more.
What? What's going on here? Ah. Okay, okay. So okay, forget about basic. I want to estimate this integral. Okay? Again, it is connected to Bessel functions, but as an example for the use of Fourier of stationary phase approximation, we want to estimate this. So now we have e to the I x times sine t minus t dt.
What goes to 0?
That's all.
What x goes to infinity?
X goes to infinity.
So f is 1.
It's x that goes to infinity.
So f is 1.
Okay, so f is 1. F is 1, and psi is
Sinus t minus
sine t minus t. So now, if psi is sine t minus t, what is psi prime? Psi prime is cosine t minus 1, and psi double prime is minus sine t. And okay, so where is the stationary point?
Stationary point is
When cosine is 1.
When cosine t equals 1, which in the limit between 0 and pi, it happens only at t equals 0.
It's in the border. We have problem. It's not problematic when it's on the border.
All what we did was when the stationary point is on the border, from the very beginning. Okay? So from here I can say that A is 0, and okay, now psi of 0 is what?
0.
Is 0. What about psi double prime of 0? It's also 0. So what should I do? Calculate the next.
Take the next.
Take the next derivative. Psi triple prime of 0 is minus 1. Good. So my estimation for that is I would like to calculate the real part of 1 over pi. Now I have to take f of a, which is 1. E to the I x psi of a is 1. E to the I pi
Over 2.
over 6. And I guess that I should have a minus because this is negative. I mean, okay. Now I have gamma of 1/3 divided by 3 over 3 factorial, which is 6, divided by x times absolute value, because I took the right of psi of 1. all this to the power
Why
of
absolute value?
1/3.
Why absolute value?
Because I put the minus here.
The minus is wrong.
The
Because you have pi over 6, but minus divided by I, so it's minus pi.
where is the I?
It's pi over 6 minus pi.
Let's
So
see.
it should be minus 5 over 6.
Okay, let's see. What we obtained here, all in all, is 6 over x to the power of 1/3, gamma of 1/3 over 3 times and we have the pi here, this pi, and we want the real part of that, which is a cosine
Of pi over 6,
of pi over 6.
which is
And do we have something else? No. Okay. Now let's see.
cosine of pi over 6 is square root of 3 over 2. If I remember correctly.
Is square root of 3
Over 2.
over 2. So all in all, I have what? I have gamma of 1/3 divided by x to the 1/3, right? And now I have pi. Now I have 6 to the 1/3, which is 2 to the 1/3 times 3 to the 1/3 divided by 3 times square root of 3 over 2. So gamma of 1/3 divided by pi x to the 1/3, and now I have what do I have? I have 2 to the 2/3, right?
Minus 2/3.
To the minus.
2 to the minus 2/3. And what about the 3?
3
I have 1/3 plus 1/2 minus 1. So it's 1/6
minus 1 over 6.
minus 1/6. So 3 to the minus 1/6. Right? Right? Exactly. Okay. So this is a correct answer. Fine? Okay. So this was, and again, what I would like to emphasize is again that first of all, it is important to take into account the points where the phase is more stationary, and I guess that you're already familiar with the fact that all the interference phenomenon in nature are of that kind. I mean, you have many trajectories, each with its own phase, either trajectories of light beams or trajectories of or quantum trajectories, path integrals, right? Classical paths, or not classical. You have many possible paths, each of them with its own phase, and at every point you have interference of many paths with different amplitudes, different phases. Usually, because you have infinite number of things, they cancel each other, right? And the only reason, and the only case where you see something is that when the phase changes slowly, so the derivative of the phase is 0, which is the case where you have a large contribution. So, for example, rainbow. You are familiar with this example, right? So, in a rainbow you have like you have a water drop, and the sun rays are entering here, and they break something like this, and then they break something like this, and get out. Of course, something get out also here, and then there is something that get out here, something like that. I don't remember exactly how, right? And the point is that you can calculate what is theta out as a function of this height above the center of the centroid of the drop, right? Theta out as a function of the height, okay? Now, the point is that if theta out as a function of the height, if the derivative of theta out of the function of the height is 0, right? In these angles, it implies that many, even heights that are very close to this one also get out at the same angle, right? And for that reason, for example, you can't see this, you can't see a rainbow if the water drop is between you and the sun, right? Because when you calculate, this is the first what we call it, entry. I mean, you see, when you look from here and the sun is here, it goes like that, and in this angle you have no place where the derivative is 0. So you just get uniform background. On the other hand, here there is a point where theta prime is 0, so you get amplification at this point, at this angle, and because this angle, this theta depends on the wavelengths, you get different angles of amplification for the different colors of the rainbow, and that's why you get you see the rainbow. I mean, for different colors of the light, different wavelengths of the light, and that's why you see the rainbow. Now, how many colors there are in the rainbow?
Depending on how strong your eye is.
7 or?
7. Okay, that's the canonical example, the canonical answer. Everybody speak about the 7 colors of the rainbow. Now, which are these 7? Please name it.
Orange, green, blue, purple, red.
Wait. Let's start from one side of the spectrum to the other, right? Red, orange, yellow,
green,
blue,
purple.
I forget something.
Who is the 7th one?
You have pink somewhere, maybe?
No, you don't have.
No.
You just have 6. And
Okay.
think about 7.
So it's a good question. How people came to define to speak about about 7 colors in the rainbow.
זה רציף.
Okay, clearly it's a continuous spectrum,
זה
right?
למה?
Clearly it's a continuous spectrum, but for some obscure reason we divide it. It's a good question, you know. But in any case, if you show a picture of a rainbow to a person and ask him to count the colors, most of people will count 6 colors that we have mentioned now. Well, where is the 7th one? So if you are Russian, then in Russian, in the Russian language, there is a difference between dark blue and light blue, which is simi,
Голубой.
and what?
Голубой, синий.
Golboy. Oh, okay. So thank you very much. So they have 2 names for the colors. Okay. For the 2 kinds of blue. So maybe it's from Russian, the idea of having 7 colors in the rainbow, although I'm not sure.
I just blame the Americans. They probably don't know how to count.
Okay. So no, okay. You have to understand that colors is a very complicated thing, right? Why? Because you have first of all you have the physics. The physics is very simple. In principle, there is a continuum spectrum of light that the eye can see, right? And you can get every combinations of stimuli from this continuum, right? You have a continuum between, who knows, 400 and 700 nanometer, right? And all you can get is physically speaking, you can get every combination from this continuum. Okay. Now it enters into your eyes, and in your eyes you have receptors. Now you have only 3 receptors, okay, with some response function as a function of the wavelengths, right? So if this is a wavelength, you have one red receptor that is like that, and then you have one green receptor that is very close to the red, and then you have blue receptor which is here, something like that.
There is a slight differentiation between the light blue and the darker blue, and between the bluish purple to the light purple. Simply, we say the light blue, we call it blue, and the darkish blue, we call it indigo. It's like we entered indigo in the middle and said this is the color.
Okay, but then so you have. If you continue, wait. Okay, this is a. There is a very simple question that I don't know the answer to. Is why people tend to identify purple as being close to red, where they are in the both sides of the spectrum.
Because
okay, you may have think if it was like so the red is here, right, and the purple is here, but there is no octave between them. If there was an octave, if red was 400 and purple was 800, red was 800 and purple was 400, then it was like this, the low do and the high do in the music.
Because
right?
of the RGB.
We do identify tones that are 1 octave from each other because when you trigger a system, usually you get all the harmonics, right? But they are not harmonics of each other. Still, people do identify purple as being closer to the red than to any other color. Now, the real mystery is in the next step. So, in the step of identifying color and naming them, right? Because
when you name colors, before there was names to colors, people couldn't see colors that well, like after the named color.
No, this is definitely, people thought about that because it was discovered, it was the so to speak, the anthropological aspect of color naming, and was discovered very much close to Darwin evolution and origin of species theory, right? And people what was discovered was very simple, that in primitive tribes, very primitive tribes, they have only 2 names for colors, which are corresponding to light and dark. So if you think they name the world only in black-white. All the dark things are black. They are under a world that is like black, and all the light colors are under words that are like white. Now, the next step is always adding red.
Because red is blood, and you see blood.
No, red
I
is
don't-
one of
red, is, red is always the third one, right? So if you are going to more developed tribes, they have 3 color names: white, black, and red.
Of course, red. Red
And
is blood.
they
It's
and
what you kill.
the next step is more complicated. So some of them, I mean, so anthropologists start wandering around all the world with a set of small, it was not plastic at the time because they didn't invent the plastic, but wooden cube, and they ask the guys in all kind of Australian and South American or Papua New Guinea tribes to divide them according to their color. And the most primitive guys divided it into 2 groups. The more elaborated guys divided it into 3 groups, so things that are dark, things that are light, and things that are red, and so on and so forth. If you give, okay. So at first, I mean, actually the first guys that discovered it did not discover it by anthropological studies, but by analyzing old books. So for example, in the Bible, you have only 3 color names, right? White, red, and black. Yes. All the other names,
Yeah, but you have
there are names,
variations.
other names, but all the other names are names of objects. It's like saying Yarok Bakbuk, right? Or Sagol Chatzi, right? You have an object and you are saying this thing has the color of that object.
Or animals.
What?
Also animals.
Whatever, right? It's like
That's one.
I want to be more I want to be more detailed than what the language allow me. So I'm using a noun or the name of an object to say that the color of this is like the color of that object, but it's not a color name, right? Color names you have only 3, and the use of the word green in the Bible, yarok, means colorful. I mean, every other color. Every other color is green.
So blue,
There is no blue.
no, but when they mean yarok, it can be blue. When they say yarok,
Yes,
it can be blue.
yes.
And stuff like
Everything that is not black, white, or red. And the same thing happens in Homer, Iliad and Odyssey. So the first guy who discovered it in the Iliad by reading carefully Homer poems. It was actually, he was a British Prime Minister, Gladstone.
The Israelis enemy.
The guy who hated the Israeli, and the Israeli hated him. So I mean, they were competing for being Prime Minister of Britain at the time. He was 4 times.
That's
He was elected 4 times to be a Prime Minister.
and Victoria hated him.
Yes, Victoria hated him, definitely. With all her heart. I mean, she liked the Israeli and hated Gladstone. And when Gladstone wrote strongly about the horrors that the Turks are doing in Bulgaria, at the time Bulgaria was under Turkish sovereignty, and they sort of had some uprising there, and the Turks Dikut or very strongly doing a lot of horrors. Then Gladstone wrote that it's horrible and we must intervene, and the Israelis said that Gladstone is worse than any Turkish horror. But anyhow, he was the first to discover it. The next guy who noted that was also an extremely interesting person from the Frankfurt Jewish community. Anyhow, but at the end of the day, I mean, so first they thought that it's a proof of evolution. That people in Australia do not have the color perception that we have, because we are higher on the evolutionary scale. But then it turns out that they clearly know what colors, what the colors are. They see the colors exactly like us. It's just that in their language they have less color terms, right? And then this raised a horrible question of whether or not color terms are something natural or something cultural. So all the the dispute of nature versus nurture or something. I mean, whether or not everything is in your genes or everything is what you was socialized into in the kindergarten is a very important. Why do we speak about it? I'm sorry. I'm wasting your time. Sorry.
Just a question about the octaves. So, if we were able to see more wavelengths, if we were able to see, okay, so for example, bees, right? Bees do see in the UV or in the IR, I don't remember.
UV.
In the UV.
Yeah.
Bees see in the UV. However, they do not see. They do not see red. They do not see red. So the question: why there are red flowers? They have no appeal for bees because they don't see them. I mean, they don't see their color. Anyhow, if you have a creature that can see in more than an octave, they can double the wavelengths or half the wavelength, whatever, yes, then presumably this creature will see colors that are differing by a full octave to be the same. I never checked if this is actually the case. You can try an experiment with birds, with bees. Yeah, sorry. With bees or whatever animals that are, yes.
אני אשאל את השאלה בעברית כי זה קשור קצת
אין בעיה.
לתרבות שלנו. ברוב העולם יש חלוקה לשלושה צבעי יסוד, RGB, כאילו רד גרין. אבל בישראל יש את השיר ילדים מפורסם באמצע היום, אני מניח שאתה מכיר אותו, וזה יצא שיש לנו חלוקה של שלושה צבעי יסוד אחרים, אדום, צהוב, כחול. תחשוב על זה. אנחנו אומרים צהוב וכחול יוצרים ירוק, אדום וצהוב יוצרים כתום, כחול ואדום.
Okay, that's a... There are two different things here.
Okay.
One of them is coloring by adding wavelengths. That's like in a TV screen. You have a screen, and from the screen you have light rays that may be either, yes, something. And in that case, people have discovered that you can generate a large portion of the visible not spectrum. I mean,
Invisible color.
At the end of the day, you have 3 receptors in your eye, right? So what your brain gets from the receptors, every receptor sends a number to the brain. Right? This number is how much I am stimulated right now. Right? So the brain gets from every region on the retina 3 numbers. Right? How much this receptor is stimulated, how much this one is stimulated, how much this one is stimulated. If all the numbers are the same, then what we see? White. So the only way we can appreciate the color is that when the 3 numbers are not the same. So essentially, if you get number for red, number for green, and numbers for blue, you can represent every color vision that you can see by in a plane of red over green, say, and blue over green. I mean, I can normalize them, because if they all are equal, I will get white. So all you are interested in here in this is this plane, right? All you can see is in this plane, and actually what's happened is that in this plane you have such a thing called color gamut. I didn't plot it exactly, but this is like a tongue. Maybe that. Anyhow, right? Now, when you add color, when you have television screen or a screen that gives you light rays, the idea is that they took 3 points here, here, and here that are red, green, blue, right? And so this allows you to generate everything which is here inside, and they want to be this triangle to be as large as you can. But clearly you cannot generate colors that are here, right? You can see them, but you cannot generate them by red, green, blue machinery.
Why?
Because you can if you have one projector that produces this light, one that produces that light, and one that produces that light, right? Then you can generate everything, only things that are in between, not things that are here. Okay? So this is the optimal. I mean, the engineers decided that this is optimal. Now, when you speak about the color of this wall, right, or the color of this of the cover of this book, right, then you do something else. Why this is yellow? Not because it emits yellow light, but it have the material here absorb all the wavelengths except the yellow. Right? Now it shouldn't be, of course, perfect. It may absorb more in blue and red, but at the end of the day it gives you yellow. So this is coloring by subtraction, not by addition. When you watch television, the colors are getting by addition. You get a light ray of this color, light ray of that color. Here you got color by subtraction. And then the three primary colors are not red, green, blue, but what you see in your printer: cyan, magenta, and red and green and something.
No, cyan, magenta, and yellow.
And yellow. Cyan, magenta, and yellow. And because the pigments are not perfect, they are adding black. If it was perfect, then cyan, magenta, and yellow together will give you black. But so this is coloring by subtraction, and it's completely different than coloring by addition.
So why every kid in kindergarten in Israel is taught about the three primary colors are red, yellow, and blue?
That's because they have a song about that. It's
yes,
not,
it's about the song. It rhymes.
Okay, so if you just want another point of curiosity in this story, it's a big story. I can speak about it hours and hours. But just to end up this hour and a half, the point is that if you search for all the colors that your eye can see, you don't find brown. There is no such color. Brown is not given by any combination of wavelengths.
But we can see brown. Brown is
That's a good point. So every brown, if you increase the size of, every brown thing, if you take it to be very large so that you don't see it on the background of something, and you shine weak light on it, I mean not low power, not many photons, you're not going to see it brown.
The brownish will disappear. You can try it in your computer.
So what
Make it
color
brown
is it?
and lower the, what they call, I don't remember, but lower
The brightness.
the brightness of
So,
your screen. You just take brown, lower the brown brightness, and you see that it's not brown anymore. It becomes reddish yellow.
So, what is the origin of
So-
there is no brown wavelength, you say?
Yes.
Yes.
Not only there is no brown wavelengths. There are many colors for which you have no single wavelengths, but they are generated by a combination of a few wavelengths, right? But brown is not generated even by a combination of wavelengths, right? It's something else.
It's generic color.
It's also olive green. Olive green is also a cheat like brown. Does not exist. For example, if you look at fireworks, right? You see all kind of colors. You never see brown. Or projector. You have never seen a projector that produces brown light. There are many kind of projectors that produce many types of light, but not brown, because there is no such color, which is interesting by itself. But okay, let's take a break. I guess we did enough examples for the Fourier integral thing, which is not a big deal after one is already familiar with Laplace integrals, although there are a few tricky points here. The idea is the same. There is a technique that generalizes the idea of Fourier and Laplace integrals, which is to take a generic integral and to change the contour in the complex plane such that it will allow you to implement the techniques of it will allow you to have either point of maximum or point of stationary phase, and then to implement these methods. But on top of that, you have to curve the contour in the of integration in the complex plane. This is what is known as steepest descent method. It is described in the book, but I don't think that we have enough time and that it's not so much important. I mean, just according to my experience. So just to let you know that such a thing exists, and you can read about it in the book. What I want to do now is to spend some time on examples of the use of the two-time perturbation expansion that we demonstrated last time, and just to show you more example. Everything is more of the same, but you know, after doing it once, twice, third time, you get some sort of familiarity with that. Okay. So what I would like to present first is the equation y d dot plus y plus epsilon times y dot cubed equals 0. And with the initial conditions, say y of 0 is 1, y dot of 0 is 0. Okay. Now, what is that physically? Okay, this is harmonic oscillator with frequency 1, I mean angular frequency 1. And this term, if we have no 3 but 1, it was what? It was a damping term, right? That if you start at 1, then you're going to do like something like that, but
if epsilon is small enough, you have underdamped oscillations, but those oscillations will die out after a long time. Okay? Now, instead of linear friction, we have nonlinear friction. Right? It goes like the velocity to the third power. Right? There are examples of such. I think that the drag force on aeroplanes is proportional to the third power of the velocity. But you can check. I didn't check it. So maybe I'm just nonsense. Okay. But for us, for the moment, this is a mathematical physics course, so we are just interested in solving that. And as before, our technique will go like that. We will write y. First of all, we will define tau as epsilon times t. Okay? And we will write y as z naught of t and tau plus epsilon z1 of t and tau plus epsilon squared z2 of t and tau, and so on and so forth. Okay? Now, and another thing that we have to remember is that d dt is actually, d dt, the second derivative with respect to t, is dou dt plus epsilon dou d tau. And by the same token, d2 dt squared is dou 2 dt squared plus 2 epsilon d2 dt d tau plus epsilon squared d2 d tau squared. Okay?
You wrote t by mistake in the previous term for d to t. No, in the d.
Tau.
Yes.
Thank you very much. Okay, so we have this equation, and we want to write order by order in epsilon to expand it. So the zeroth order is z naught d2 z naught dt squared plus z naught equals 0. And the answer is a of tau e to the it plus a conjugate of tau e to the minus it. So the important thing is that a is allowed to be a function of tau. Okay? Now, we take this, and now we are going to write the second thing. This is order epsilon to the power of 0. Now we want things that are order epsilon to the power of 1. So first of all, we are going to have d2 z1 dt squared plus z1 is equal to, okay? And now we have, first of all, we have y0 dot cube. So we're going to have a e to the it, but I have to take the derivative with respect to t, not with respect to tau, because the derivative with respect to tau gives me another epsilon. So I have ia e to the it minus ia star e to the minus it cubed. Okay, what else? This is the first thing. And we have also this thing, right? Which is minus 2.
The first one should also be the minus.
Yes. Thank you. And here we have minus 2. And now I should take the derivative of this garbage with respect to t and tau. So I have I do a do tau e to the it minus I do a star do tau e to the minus it.
Okay? Good. So, and as I told you, we do not really calculate the first order correction. We only check what are the conditions in which, by which we have to satisfy in order to the first order equation not to blow up, give us a solution that blows up. And this will give us the form of A of tau. That's a trick. Okay? So, because this is harmonic oscillator with angular velocity 1, omega is 1, right? Then everything that have frequency 1 in this expression will get into resonance with it. So we want to avoid resonances. So we want to kill everything that is e to the it or e to the minus it alone. Okay, so what will give us contribution, right? So for example, what will be the coefficient of a e to the it in this expression? First of all, we have from here minus 2I do A, of e to the it, not of a to the. So, what are the coefficient of a to the, e to the it? So minus 2I do A do tau. Minus 2I do A do tau.
Yeah.
Right? This is the contribution from here. Then we have a contribution from here. Now we have, we should take 2 of these and 1 of that. Right? So we have first of all we have a factor of 3. Okay, I will write a plus here, or let's start with the minus. This is that minus.
Yes.
Okay? I have 3, and I have 2 of these. 2 of these will give me plus, because I have I squared, and I have a squared. And 1 of these. So this will give me again minus I and a star. That's it. Okay? So to avoid resonance, this should be 0. Of course, the e to the minus it thing also should go to 0, but it will become automatically the complex conjugate of that. So we only have to take care of this. This should go to 0. Should be 0. So what we have obtained is an equation for A do tau is equals to minus 3/2 A absolute value squared times A. Note that it's very close to the equation that we got last time, but there are differences in the i's. Then it was, I think, there was a relative I between the two. Okay? We still continue with the same strategy. So what we are doing, we will calculate, assume now that A is R e to the I theta, both of them functions of tau. And we plug it here. What we are going to get is do R do tau plus I R do theta do tau is equal to minus 3/2 R cubed. Where the e to the I theta cancels out. These are two equations. One of them is R and theta are real. So this is the imaginary part and this is the real part. We have to make sure that both of them are 0. And this implies that theta is a constant, say theta naught. Theta is not changing over time. Whereas R satisfied, do R or dr over R cubed
is equals to minus 3/2 d tau. Okay? What should I do? I want to solve it. So I'm integrating over both sides. So I have minus 3/2 tau here. And the integral over 1 over r cubed is 1 over 2 minus 1 over 2r squared. Okay, so we are from r0 to r of t, of tau, sorry, of minus 1 over 2r squared. Right? Which gives me 1 over 2r naught squared minus 1 over 2 r of tau squared. So 1 over 2 r of tau squared is, I'm taking this to the other side, so both of them are plus, are positive. So I'm taking this to here and this to here. Right? So both of them are plus. And I have 2 r naught squared here. And here I have 1 plus 3 tau r naught squared. And therefore, the 2 cancels out, and I find that r of tau is the square root of r naught squared divided by 1 plus 3 tau r naught squared. Right? And when tau is 0, this is r naught. Good. So now I'm taking all this monster and I would like to plug it at z naught. So this is the solution for A. So clearly now A will be so therefore Y or Z naught, if you want, Z naught, which is the first order, right, is square root of r naught squared divided by 1 plus 3 tau r naught squared. Okay? Times e to the I t plus theta naught. Tau plus t. No, that's t. This is t. Yes, because theta naught is independent of tau. It's just a number. Right? And we want to take actually the real part of that. 2 times the real part of that. Right? So I have a factor of 2 here. And here I have cosine of t plus theta naught. Okay? And now I can change tau back to epsilon t. Right? Epsilon t. And I would like to find out what is the I would like to satisfy the boundary, the initial condition. So this is now, I can write it as y. The initial conditions are y of 0 is 0. So what is y of 0?
Y of 0 is 1.
Is 1, sorry. So y of 0 is t equals 0. So this is 2r naught times cosine of theta naught. Now, what is y dot of 0?
First we'll find y dot.
I have to take the derivative of that with respect to time. Okay, now,
First of all, I have the cosine. I can take the derivative of the cosine. So I will get minus sine times of t plus theta naught times the square root. This square root times 2. Okay? And the square root is r naught squared divided by 1 plus 3 epsilon t r naught squared. And then I have another term. But the other term will come from the derivative of that, so it must have another epsilon. So it will be negligible in the limit we are taking, right? And therefore I can take only this term and plug t equals 0 to get what? To get 2 minus 2r naught times sine of theta naught. This must be 0. Okay? So the only choice that I have is theta naught equals 0 and r naught equals 1/2. And therefore, my solution is for y is what? Is y of t equals to 2 times square root of r naught square is 1/4, right?
Okay. Yeah.
So the square root of 1/4 is 1/2, so this will go away, and I will have 1 plus 3/4
No.
epsilon t times sine
Cosine.
cosine. Which implies that we have oscillations that are exactly like the oscillations that we had before, but the amplitude of these oscillations is going down like 1 over square root of t. Right? It goes down like very slowly, very, very slowly. Okay?
Epsilon goes to infinity or?
No, epsilon goes to 0. Epsilon is small, a small parameter. Right? But on time scales that are order epsilon t, I will see an appreciate decrease of the amplitude of oscillation.
Question.
Yeah.
Are theta always gonna be constant?
What?
Theta is always gonna be constant?
No. Last time it was not constant. And last week.
It was also constant.
No,
It
has
was
the.
different constant, but it was also constant.
It was constant? I don't
Yes.
remember.
We just got another constant, but it was also constant.
No. Last week it was. No. Last week theta have we had a phase. Last week we had a phase here. Theta was not a constant. Okay. So this was an example that is very similar in spirit to what we did last week. Let's make another. Let's take another example that is less similar. And this is Rayleigh? Yes. No. Yes, this was a cubic damping. Okay, I didn't check. Rayleigh oscillator satisfies y d dot plus y equals to epsilon times y dot minus y cubed over 6. Y dot cubed over 6. Y dot. Okay. What does that mean? Suppose I don't have the cubic term. What the linear problem corresponds to?
To regular now.
Harmonic oscillator, but it's not friction, like negative.
Anti-friction.
Yes.
Anti-friction. So, if we do not have the cubic term, then we will get harmonic oscillator that is going out without any bound. Okay? However, we have the y dots cubed, so the cube term will stop the growth. Okay? And the question is how we can see that. Again, what will be the initial conditions? The initial conditions will be y dot is 0, y of 0 is 0, and y dot of 0 is, for whatever reason that I don't understand, 2a. Whatever. Who cares? Good. The problem is that if you start at 0, you never get out. 0 is the solution. Good. So, next, what we would like to do, okay, same story, blah, 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 blah. Now we can write it immediately, right? I will write it below that. Okay, so z naught will be again a of tau e to the it plus a star of tau e to the minus it, and then we have d2 z1 dt squared plus z1 equals to, okay, now that's, okay, so I have y dot. Now y dot, I want to take the derivative with respect to t only, right? Because I have an epsilon outside. So I want the derivative with respect to t only. First of all, I have this. I have the two. This term. So I have again minus 2 times do a do tau I do a do tau e to the it minus I do a do tau e to the it. E to the minus it. This is not from the this term.
Do a star.
Do a star, yes. This is not from this term, this is from that term. Okay? And now I have to collect things that from the term to the right, but because I have an epsilon in front of it, I will take only terms that are zeroth order in epsilon. So I will have plus y dot, which is I a e to the it minus I a star e to the minus it. Okay, just derivative with respect to t. And we have minus I a e to the it minus I a conjugate e to the minus it cubed. Again, I would like this thing to have no resonance. So again, let's collect the coefficient of e to the it. What are the coefficients?
Minus 2i.
So we have the minus 2i do a do tau
Plus
Plus IA.
plus ia.
minus.
Okay, now, okay, minus.
You need to divide by 3. You forgot to divide by 3.
Yes. Minus 1/3 of 3, 2 times that and 1 times that. So the 2 times that give me I squared, so it becomes a plus. And then we have a squared. And then we are taking 1 from this side, so we have again minus. This becomes an I, and we have a conjugate. So this is a thing that should go to 0. Okay? Note that we have, so the 3 and the 3 cancels out, and the i's
are going away. So our equation is dou A dot tau is equals to 1/2 times A minus A cubed. Minus A squared times A, or let me write it like A absolute value squared times A. Now, as usual, A is R of tau e to the I theta of tau, and I can write it as dou R dot tau plus R of tau I dot theta dot tau is equals to 1/2 times R minus R cubed e to the I tau goes away. Again, though this term must vanish, so theta, we have already solved that theta is theta naught. Theta is tau independent. Okay? What remains is the R d tau is 1/2 R minus R squared. How do you solve that?
R cubed.
R cubed. So, R minus R cubed.
Integrate one.
What?
Integration of the one.
Yes. So, but in any case, the solution is R equals to okay. So if I'm taking tau to 1, it will be R naught. Tau to 0, right? Or I can write it as R naught divided by e to the tau plus 1 minus e to the tau R naught squared to the power of 1/2. Is that true?
Shouldn't it be R naught squared?
E to the minus tau here. Is that
Tau
true?
over 2.
What?
Tau over 2.
No, because you have the 1/2 here.
Ah.
I multiplied the numerator, the denominator by e to the
Tau over 2.
tau over 2. By e to the minus tau over 2. Okay. So, all in all, what I have here is so I did find R and I want to, okay.
Like the
So
initial condition.
Y is,
I think it's in a minus.
Minus.
Over it's e to the minus tau 1 minus e to the minus tau.
yes, right. 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 So we have this R times e to the minus tau plus 1 minus e to the minus tau times R naught squared times
One.
what? Times 2 cosine of t plus phi,
You forgot the square root. The denominator.
1/2. 2 cosine of t plus theta naught. Exactly as before. Because we plug it into the A and we take the real part, blah 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 blah. We got that. And now we have to plug in the initial conditions. So what are the initial conditions? First of all, we want y of 0 to be 0, meaning that 2r naught cosine of theta naught divided by, now if tau is 0, then this is 1. The denominator is 1, so this is 0 for y of 0 to be 0. And what about y dot of 0? Y dot of 0 is 2r naught times sine minus sine of t plus theta naught divided by this denominator, right? By this. And again, I have to add derivative with respect to tau here. But as before, this will give me another epsilon, because tau is epsilon t. Okay, maybe I should write it now as epsilon t. Right? So I can neglect it to the first order in epsilon, and what I get is that 2a must be equal to minus 2r naught times sine of theta naught. So these are my initial conditions.
Theta naught should be equals to pi over 2.
Therefore, theta naught must be equal to pi over 2.
And r naught is minus a.
And r naught is minus a.
But it doesn't necessarily. It can be that sine theta naught is minus 1 and cosine theta naught will be still 0. So it's plus. It's like plus minus a.
Yeah, who cares? I mean, just the initial phase. So all in all, what we did find is that what? How the solution looks like? Here. I should plug everything here. Right? So what I will get is y equals to 2a up to the sine, right? Cosine of t minus pi over 2, if you want to do it your way,
Just sine.
divided by e to the minus epsilon t plus 1 minus e to the minus epsilon t times 2a.
2a?
4a squared.
Why 4? Why 4? A squared.
R naught squared. R naught is a, so a squared.
I think that the cosine t minus pi over 2 can be written as sine t or minus sine t.
Whatever.
It's
Okay.
nicer.
Now, what's important is that y of 0 is 0, right? Y dot of 0 to the 0th order in epsilon is 0, okay? And now the question is, what is y at infinity? If I'm waiting infinitely long time, what should I get?
The numerator is bounded, so and the denominator.
So when as t goes to infinity, much larger than 1 over epsilon, then this is 0 and this is 0. So I have in the denominator, I have a.
Yes.
So as t goes to infinity, this goes to 2
2 sine t.
cosine of t minus pi over 2, if you want sine, whatever, right? Meaning that there are finite oscillations.
Yes.
You see? You have 0 oscillations. I mean, you start very close to 0 with this small velocity, and as time goes to infinity, you end up with finite oscillations that are not growing and not shrinking. This is because the balance between the negative friction and the positive nonlinear friction.
Yeah, if negative friction will be in the second power or third power, the answer will be the same?
If the negative friction will be in the second power, yes. If it will be in the third power, then I mean they are the same term.
Okay.
I mean you want, in order to get such a behavior of finite oscillations, you want the negative power, you want the negative friction at small oscillations and positive friction at large oscillations.
Yes.
This, everything, every combination that will satisfy that will give you such a behavior. Also, let's take another example that is very similar, which is so epsilon times 1 minus y squared times y dot. What's the trick here? If y is very small, then the y squared is negligible with respect to 1. In such a case, we have negative friction, and the amplitude of oscillation will go up. If y, however, if it go up, y becomes larger. If y is large, then we have a positive friction, right? So it's a very similar thing. So similar that it is actually, if I remember it correctly, it's actually the same. So let's erase this and check what we will get when we collect the terms to first order. Zeroth order in epsilon is of course the same, right? So we want the first order in epsilon, and we have that. We have this equals to, now we have minus 2 IA e to the IT minus IA star e to the minus IT, the standard thing that we have from the actually the free part. And now we have 1 minus, we have y dot plus y dot, which is IA e to the IT minus IA star e to the minus IT times 1 minus y squared. So I have 1 minus a squared e to the 2it minus 2a absolute value squared, right?
Yeah.
Minus a star squared e to the minus 2it. That's it. Okay? And again, we want to find out what are the coefficients of the resonant terms, which are e to the it, e to the minus it. And again, because they are complex conjugate of each other, we can look only for one of them. So let's look for the e to the it. What are we going to get?
Wait, something is wrong. You should have derivative of A.
No, because this is y squared.
Yes, but not here, in the y dot.
In the y dot I took a derivative. Here, I minus I.
But you should have dou A dot.
No, you shouldn't, because
Oh,
it's
they're
getting you
getting
another epsilon.
Sorry, the dou dot tau is here.
Okay. Somewhere you should have.
Yeah.
Otherwise, you just
Yes,
get
of
A
course.
equals number.
The dou dot tau is the standard. Okay. So, e to the it, what are the coefficients? Minus 2I do A dot tau, from the first thing.
Plus A.
Plus
And now we have to collect the garbage. So, the 1 and this will give me what?
plus
IA.
IA.
Plus IA. That's it?
No, no, that's it.
That's it. And
Minus
now,
Y
okay.
plus-
Can I get some e to this times that? Okay? This times that
Plus I.
will give me
Plus I.
Plus I.
plus
A squared.
I a squared 8 star. Yes?
And you have minus I.
Wait. We had this one, right? That's a contribution of the one. This one gave us a contribution with that. Okay? Now, this one
Doesn't
Yes,
give
you
us
can
any
choose.
contribution.
will give us a contribution with that.
Yeah, but it's in it's
Why?
minus.
It will be minus. So the only other term is this one with that. What this will give us?
Minus 2I.
Minus.
Yes, minus, because you have minus here.
Minus
there.
2.
Minus 2
Minus
I.
2I A squared.
Minus 2i
I.
A squared.
a absolute value squared
A.
a.
You can now stop.
And so all in all, we have do a dot tau is equals to
1/2.
all the i's are going away. I have 1/2 of a minus a squared a.
No. Wait. I think it's other way around.
What?
It's other way around, I think.
This is,
Because it's negative.
I took that to the other side,
Oh, okay. Yeah,
and
yeah,
I have 1/2, that's 1/2, a minus, yes.
yeah.
Okay. So I think that this was exactly what we
Yes.
obtained before. Okay? So the answers are the same. Okay? So this is called van der Pol. Van der Pol oscillator. And both this and the Rayleigh oscillator are examples of a system that supports a limit cycle. So it will start here. Okay, if I'm plotting it is y and y dot, right? In the position velocity plane, it will start here and will do something like that, and then it converges to stable oscillations. Okay? Good.
But when you have just negative friction,
If you have just negative friction, then it blows up to infinity. It's not physical.
I mean positive friction.
If you have
So
just
this
positive
is
friction, it
also-
stays at zero. It will at infinity it will be at zero. Y equals 0 and y dot is 0.
Yes, but it's also the same type of.
No. I mean, growing oscillation that saturates at a limit cycle is something, right? So in physics, in fundamental physics, in Hamiltonian physics, right, you can describe only two types of equilibrium scenarios. Okay? You may have right? There are two equilibrium scenarios. If your potential is like that, right, you may be here, in which case, around this point, you have stable oscillations. So if you plot it, for example, in the x P or V, whatever, right, plane, if you start here, you have something like that. Around it, you're doing something like that. This is called the center. Okay? And now, what's happened if you start here?
Unstable.
What?
Just it's unstable.
Here it will be unstable. So, okay, the best way to think about it is to think about the double well, something like that, right? Which implies that you have a center here, and you have a center here. Okay? But if you give the system exactly enough the velocity, it will reach to here and stay here, but this is an unstable fixed point. So if you think about it a little bit more, you find out that you have something like that. Right? And then above it, in higher energies, it is doing something like that. Now, such a point is called a center, and such a point is called a saddle. Like
Graph.
yeah.
Like a saddle.
Like a saddle. Okay? And these are the only fixed points that you have in Hamiltonian physics. The only equilibrium scenarios of the system. Right? You can have many other things. First of all, attractive and repulsive fixed points. So, movement like this. If you have friction, you have something like that. That's friction. Everything converges into here. This cannot be the case because of the Liouville theorem. Liouville theorem states that the volume of a phase space droplet is kept fixed under the dynamics. And here you see that if you start, you have many points here, then they will all then end up here. So it shrinks.
This has happened.
What?
This has happened in real life.
Yes, and this is because friction is not physics. I mean, friction is prohibited by the physics, in the sense that by saying friction, you're saying I'm throwing kinetic energy into degrees of freedom I am not interested in. Right? I'm doing something like that. I'm rolling a ball here and it stops. Why it stops? Where the kinetic energy goes? It goes to the temperature of the damn thing. And this, what is temperature? Temperature is the kinetic energy of the molecules from which this piece of metal is made. Right? And if you will take them into account, you will find out that you have only this. Right? So this is like what's happened when you throw out some of the degrees of freedom you are not interested in them, you may imagine you get something like that. Right? So this is an attractive fixed point. Of course, you may have a repulsive fixed point. Attractive and repulsive may also be, like that. If you have overdamped, this is like underdamped oscillations. You are still doing oscillations, but they are getting smaller and smaller in amplitude. This is an overdamped oscillation. You just go directly to the fixed point, and you may have also, something like that. But these all are fixed points. If you think about the possible manifold, you also have something like that, which is a limit cycle. Limit cycle is not a fixed point. If you started here, then you move to here, to here, to here, to here, but you never leave the cycle. Right? So these are examples of fixed points. There are two fixed points that are allowed in fundamental physics, which are saddle and center. If you are doing more, if you expand your view to systems like this, you can find also attractive fixed points, repulsive fixed points, and another thing which is a limit cycle. So a system with a limit cycle is a system that gets into a state in which it sticks to the cycle, but it moves and it's a periodic motion. right? And what else you have in physics? Okay, what else you have in physics? You have systems with fixed points, with attractive repulsive fixed point, you have limit cycles, and
Chaos.
chaotic attractors. Thank you very much. So a chaotic attractor, for a chaotic attractor you need 3D, but in 3D you may have something that, okay, I can't of course plot it, but a trajectory that is moving in space and never crosses itself. This is something that I cannot plot, but it never crosses itself. Because, but still it is moving in a finite region. It do not escape from a cube, but it never crosses itself. Right? And these are the only, yes, these are the only motions that are allowed by, not by nonlinear, for nonlinear systems in general.
It's not that it doesn't crosses itself, it's just you don't really know when it crosses.
No. It never cross. If it was crossing itself, then it was a limit cycle. Actually, nobody, I think, as far as I know, nobody have proved that the famous examples of chaos, like Lorentz attractor and so on, are not very, very, very long limit cycle.
Yeah.
Right? It still may be that everything is limit cycle with periodicity 10 to the 10, and no matter how long you are going to track it or simulate it, you will not figure it out. But yes, so this is that's the chaotic attractors are, but for any practical purpose, right? They are doing something which is completely random, chaotic, and they do not cross themselves. And this is possible only above 2D. So you have attractive fixed points, you have actually the fifth chapter of Bender and Orsag is devoted to all this classification. I didn't have time to, just on the level of telling stories, I can elaborate on that. You know that this was the original excuse for spending money on computers.
Can you define
Yes, you told us.
Yeah.
Can you approximate the volume of the chaotic attractor? Like if you have a chaotic motion, can you define a volume?
It has a fractal dimensionality. You know, it visits.
A volume in which
it's not a one. It's not 2 dimensions. It's 2 plus epsilon dimensions and all things. I mean, these things were extremely popular many years ago when the study of chaos blows up. I think it was in the 80s. If you read the book of James Glick, Chaos, he published it, I think, in the late 80s, something like that. These were the glorious days of chaos. Many physicists turned to study chaos, and it was extremely popular. And it took, like, you know, it stayed like that, like for about 20 years or so, maybe 15 years, where it was an extremely popular subject, and you know, tons of seminars on all the mathematical peculiarities of chaotic systems, and there are tons of such peculiarities. And then people realized that there is nothing to do with that, actually. They had a promise. The promise was what they wrote, you know, in the first paragraph of the research proposals, is that by studying chaos, they will have, they will find a way to control the chaos, And this will allow them, for example, to make the dynamics of a heat engine much more efficient, because they will control somehow the horrible mass that happens there when the things blow, when the gas burn and blows up and so on. So this was a promise. There were other promises, and they all, I think, did not fulfill themselves. So slowly but continuously, people start living these issues, and nowadays it's very difficult to find a physicist who is saying, I'm doing chaos, right? It's all the, I mean, of course there are chaotic systems, and there are many cases in which you want to study systems that have chaotic behavior and to learn something about that, but to deal with chaos as a topic by itself without the context of another physical problem is something that is kind of rare. Some people are still doing that, but not many. Not by far, not as many as
What people are promising today. So
What?
What people are promising
you
today.
see, now, for example, in the last few years, the story of quantum computing becomes extremely popular. How much this is going to stay around, I mean, no. People are speaking about quantum computing ever since the 80s, even before. But the technology is advancing, so they did quantum computing with 2 bits and then moved to 3 bits, and now the technology, apparently the basic technology is advancing in quite a decent pace. There is still a good question of what all this is good for, because a quantum computer is not better than traditional computer by any means, except of, quantum computer is better than traditional computer
Quantum
in
tasks.
in 2 things that are decomposing numbers to the rational, the prime factorization, and sorting long lists.
Also in
I don't think that
simulation.
what?
Also in simulating quantum
Yeah, okay, but this is like doing an experiment. Who cares, right? And then there are other tasks that were invented in order to justify. I mean, you read in newspapers that Google quantum computer made calculations that will take 2 to the 10 to the 100 trillion years for a normal computer, and they did it in 5 seconds.
No.
What?
But do we need this calculation?
No.
Yes, but what they do not tell you is that this is a problem that was invented intentionally in order to be triggered by quantum computers, and it has absolutely no value for human beings. So there is still some people are saying that we are facing in a few years what they call quantum winter, which is people will understand that there is nothing to do with quantum computers and will leave the topic. I'm not sure, because once you have
You can do one thing, and this is teleporting from another place to from. If you can scale quantum computing to, if you say that you are yourself a quantum computer, you can teleport yourself in a manner.
Okay, let's see.
Probably the usage will be for crypto.
Yeah, for cryptography it will be very important in the sense that it will kill all the algorithms used today, and you will have to move to another thing. But okay, whatever. For what it works. Okay, so what? I mean, it's an interesting thing that, I mean, there are these books of Feynman, right? So Feynman gave a physics course in Caltech in 1962, 63, 64. It was 2 years, and then in 64 he gave another few lectures. And then in his, and he sort of tried to cover not all physics. It was an undergraduate course, right? But it's very wide, and he tried to cover all the topics, the main topics in the undergraduate studies of physics. And during this course, he pointed out quite a few times, I guess not less than 10. I'm not pretending to say that I remember all these points, but he pointed out quite a few times problems that were unsolved at his time. That has to do with, you know, finding theoretically the magnetic properties of materials, or what material is going to become a superconductor at low temperatures, or weather. Why the clouds are charged? Why the hell the clouds are charged? It's such a mystery, unbelievable, and so on. In all around there are mysteries. I think that none of these mysteries was solved ever since.
If you ask me, I think that in some areas the mysteries will be solved, but then we need to find applications to all the mysteries that we solved.
No, they're very simple. If you can, you know everything about an atom. Right? You can write Schrödinger equation, even if there are relativistic effects, you can take them into account also, and you can write the Schrödinger equation for an atom of iron, and for an atom of nitrogen, and for an atom of, I don't know, platinum, right? Iron and platinum. Now, given that, you would believe, I would believe in a priori that given this knowledge, there will be no problem to predict the magnetic behavior of iron, which is completely different than the magnetic behavior of platinum.
Yes, of course.
Completely different, right? It's unbelievably different. Nobody knows how to do that.
But
Ex post facto, of course, everybody are smart. I mean, they can tell you, yes, in iron there is a strong exchange interaction, blah, 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 blah. Okay, so now I will give you a new message. 20% iron, 80%, 20% nickel, and 60% gold. What they are doing, they produce the message, and they measure the magnetic properties. There is no, you know, smart physicist in the University of who and who that will get the, you know, just the composition, and by knowledge what the atoms are will provide you with their magnetic properties.
Because it's
not even, you know, not even with I think, not even with the crystal structure. Not to mention the magnetic properties, not to mention the electronic properties, like becoming a superconductor at low temperature. Nobody knows. And you know, the potential applicativity of this is infinite. Is infinite. You will be able, if you can do that, then you can design materials that will have fantastic uses. But
because something chaotic goes there and you cannot predict it.
What chaotic in
I don't know, but
what
something.
is chaotic
something
in iron?
But something. If you have a perfect theory, it should applicate perfectly in real
No,
life.
because you don't know how to solve a problem with 500 electrons. Maybe with quantum computing, you can simulate it. I mean, here is
Quantum computers have one.
but this is like making an experiment. You see?
Yeah, but quantum computers should have one superiority about on regular computers is the fact that they can solve differential equations faster because they are functions in their
No, they can solve only if I know. Maybe I'm speaking nonsense now, but to the best of my knowledge, they can solve faster only the differential equations that are dictating their dynamics.
Yes.
But by the same
you can
token, you
change the
can say
dynamics
that if
however
I'm
you
throwing
want.
a ball from the window, it solves the differential equation. Of course, it solves the differential equation, but who cares?
But you can
Okay.
dictate the dynamics however you want.
Anyhow, so just to conclude, let me mention a problem that I'm not going to solve, but just to make you, to remind you, which is the problem of y d dot plus y, right, is equal to, say, minus 2 epsilon times cosine of omega t times y. Now what is that? You see this equation?
Force?
No, because it multiplied by y.
Ah.
See?
Yeah.
So this is actually, although it you can't see the. Okay, you have a kid who wants to ride the swing, right? If the kid is 3 years old or 2 years old, then you have to stand by and push the swing every time it's right. And so this is a forced oscillator,
Yes.
right? It's like this is like y d dot plus y equals to f times. Now, okay, what you actually are doing is you kick it every time the swing gets to your hand. But this is automatically gives you a resonance, because if you make a Fourier transform of that, if you decompose it into frequencies, of course the main frequency will be that frequency, which is exactly the frequency of the swing, because this is when you have your kid coming back, right? So it's a forced oscillation. But if the kid is a little bit more mature, then you can save your effort by teaching him or her to swing his legs. Yes, great. And so why swinging your legs helps you in riding a swing? Right? That's a very good question. Because you know that you can't move. I mean, the net force you apply is 0, right?
Yeah, but you change center of mass.
You change then what? So what you are actually doing when swinging your legs, right, is changing, as you say, changing the center of mass. So this is like exactly like if you have a swing, changing the I mean, if you have a pendulum like that, right, taking this point up and down,
Yes.
because you are changing the effective length. I mean, you have square root of g over L, and now L depends on T, because L is the distance from the point in which the swing is connected to the center of mass. So you increase and the position of the center of mass is going up and down, and this gives you something like that. And if you expand it, you will get something like that. Right? And the trick is, okay, so suppose this is the equation. This equation is very important. It has a name. It's called Matthew equation. And if you, it's also Schrödinger equation, the time in, if I will write it like that, right? You will identify that this is actually the equation for a particle in periodic potential, right? So okay, so what will happen now if we will try to implement the naive perturbation theory? Not the two-time, the naive one. Right? So in the naive one, we are going to write y as y naught plus epsilon y1. And when we plug y naught here, we get y naught d dot plus y naught equals 0. So y naught will be some, I don't know, a times e to the I t. Again, you have to take the real part, but just to make the calculation easier. Right? Or maybe I want to write it like why do I did that? I don't know, but let's write it as a, yes, a to the e to the it. I don't know why. For some reason I wrote it in all its glory, but I don't know why. Okay? Fine. And now let's plug it. So what will be the first so what we have is y not d dot plus y1, sorry, y1 d dot plus y1 is equals to 2 epsilon times e to the I omega t times, maybe this is because it is nonlinear. Okay, let's write it as a to the it plus b to the minus it. This is y naught. So this will be e to the it plus e to the minus I omega t without the 2, with the minus, right? This is the cosine. And I would like to multiply that by e to the it plus e to the a to the it plus b to the minus it. Right? Okay. So, what is the condition for resonance? What is the condition for resonance? You see, I have the frequency here is 1. I can write it even as omega naught, if you like. Right? Let's write omega naught squared here, and then I have omega naught squared here, and omega naught squared here, and I have here e to the I omega naught t, and here e to the I minus omega naught t. Right? And this is omega naught t, and this is omega naught t. Right? Just I took omega naught is 1, but this is for general case. What is the condition for resonance?
Omega is 0?
No. Omega naught is given.
No, omega, not omega.
Omega is omega is
0 or
no. Omega is 0. Omega is 0 means that you implement a fixed force.
Yes.
Right? So I'm speaking about non-zero omega.
equals omega naught.
So what I want is that omega plus omega naught or omega minus omega naught will be equal to omega naught. Right? So the conditions are omega plus minus omega naught equals omega naught, which is either omega equals 0, that is not, or what's more important is omega equals to 2 omega naught. Right? This is a condition for a resonance. And this is exactly what your kid is doing when riding the what you call the swings, because note that in every next time you are trying it yourself, note that in every full cycle of the swing, right?
Yeah, you need to.
You're doing something like that and like that,
Yes.
right?
Yes.
So in every period of the swing, the center of mass goes down, up 2 times, right? Next time, okay, and this is exactly the resonance frequency. Okay, so if you perturb this is called the parametric oscillator, parametric resonance. So you get parametric resonance when omega is 2 omega naught. Now, suppose that omega is not 2 omega naught, so you can solve it, and this will be okay. However, if you expand it, if you now try the next you will find that when omega is equal to and you find that in higher order perturbation theory you can find other, I don't remember exactly what are the relevant numbers, but other resonances, right? If you want, I mean, it's all written here actually. There are resonances when omega naught squared is omega naught squared is n squared over 4 omega naught. Omega. So omega, yes. So this one is a case where if n is 1, then omega naught squared is a quarter of an omega.
But it should be omega naught squared equal to n squared over 4 omega squared.
Let me see. Maybe it's omega. No, it should be omega. Wait.
גם היחידות כולם מסתדרות.
What about the units? This is not good. You're right. So this is omega squared, and this is okay. Let's take omega to be, if omega, okay, for omega is 1, if omega is 1, you get resonances with, okay, so if omega is 1, for example, then the resonance is that omega naught is 1/2. So omega naught squared is 1/4. Right? What about the units? I'm not sure. Okay. So in any case, okay, so you can actually also write the swing with another. Of course, this is a stronger resonance, the strongest resonance.
but you can also write the swing with a different protocol of tilting your legs.
So what's the strongest?
This is the strongest resonance. And actually, if you tilt your legs in the right frequency, you can also stabilize, as I told you, the swing, the top. So if you take the swing like that, right, you can stabilize this scenario, but I don't recommend to do that in actual swings, but it can be done. That's a capita pendulum. Okay, I think that we have no time to continue with that. So that's it. This was a course. I do appreciate your participation because most of your friends decide not to participate. And
לפני כמה שיעורים פתחתי את המודל, ראיתי שיש איזה 30 אנשים בקורס, הייתי בעד.
כן, אבל עכשיו השאלה אם ה-30 האלה עזבו את הקורס או שהם פשוט רואים את ההרצאות בזה ו...
לא זה ולא זה.
מה?
לא זה ולא זה.
לא עזבו את הקורס ולא רואים את ההרצאות. טוב, בשביל זה יבוא מבחן ויגלה מי ידע את החומר ומי לא. אז בהצלחה, good luck for all of you in the examination and see you here and there.
Thank you.
Thank you very much.
היה צנוע.
צריכים להגיד מראש, אתה סימון?
כן.
כמו שאתה סימון ישראלי, אתה רוצה למחוא כפיים, אז תגיד לשער, אבל לא נמחאו אחרת בנחיתה.
שתי שדות חלשים,
לא צריכים להיות מעורבים בעניין.
מדבר על
הכל כזה פרוצדורה.
מדבר על ישראלים, ואתה לא אומר להם.
תחשוב שיש לך שתי כוכבי לכת ממש משהו.
כן, כן, כן.
ואז יש את הצורה הגבול שבאמצע.
קשור לכאוס.
ועניתי לאחד הפחות שווה, עניתי לאחד שרצה לוודא
ממש לך באמצע, בצד שני.
אם יש משהו שלא מפתיע אותי בצד זה,
הם גם צריכים כאילו, זה מרגיש כאילו הם תיאמו את השעה שלי.
כן, זה קשור.